Hey, P-Calculus. This video is all about lesson 2 of section 1.1. So I split that up into 2 different days of work. This one's going to be heavy on just understanding how functions work within the context of graphing. And there's also going to be a couple word problems towards the end that's just going to kind of challenge our thinking a little bit. So, getting started. We've got a grid space behind us. I'm going to do about 6 graphs to get us back into the swing of things. So the first one we see is y equals 2x squared minus 1. You guys should recognize that that's a parabola. Usually parabolas have the context x minus h squared plus k. If you remember, that tells us all about the shifting. And there's usually an a term in front of that. So the a tells us whether or not it's going to be a skinny graph or a wide graph. The A also tells us whether or not it's going to be facing upward or facing downward. The H is going to be how far it shifts horizontally, left or right. The K represents how far it shifts vertically, up or down. So at this point, it looks like we have no left or right shifts because there's no grouping symbols outside of the square. The 2 in front of the A, though, is going to make it skinnier, and the minus 1 is just going to shift it down 1. So a regular parabola looks pretty much like this. We're shifting it down 1 and then making it skinnier. So the down 1 right here. You know what? You can just plug in points to check things out. So if we go x equals 1, then you're squaring 1, which is 1, times 2, 2. 2 minus 1, 1. And you should also keep in mind that all parabolas are symmetrical, which means that if this is the place, if this is sort of like our axis of symmetry, then you just have to move 1 unit to the other side of that axis, and you've got a partner point. It lets us plot points a lot quicker. So then if you try 2 over here, you plug in 2 for the x, squared is 4. 4 times 2 is 8. 8 minus 1 is 7. So you go over 2, up 1, 2, 3, 4, 5, 6, 7. And then move 2 units from the axis of symmetry to the other spot. And you got a parabola. So just make sure that, like, this is really the important piece that I want us to kind of unearth from when we learned it back in pre-calculus times. All right, 47. Now this one is going to be very different. X equals 1/4 y squared. Now, I really didn't challenge you in this way last year for pre-calc. Like this whole idea of what happens when you get a y squared instead of an x squared. Well, what we can do is we can actually solve for y and look at it from the perspective of, if I get y by itself, maybe it'll make more sense. So I'm going to rewrite this as 1/4 y squared is equal to x. Is that showing up? Okay. Here, let's give it a little more. There we go. And we can actually multiply this 1/4 to the other side. Like multiply by 4. We'll cancel out the 1/4 here and be attached to the x. So we got y squared is equal to 4x. Square rooting both sides allows us to solve for y. But remember, when you square root both sides of an equation in which any variable is present, you have to keep in mind that the plus or minus situation can occur. And really from there, we can actually compute square root of 4. It's 2. But then leave the root x in there. So this is interesting. We've got a square root function that is both a positive and a negative. Actually, it's 2 square root functions. So this is y is equal to the positive 2 root x, and y is equal to the negative 2 root x. Now, if you recall, root x started at the origin, and it shifted left or right whenever it had the x minus h structure involved in the root symbol. This is no different. So if I'm graphing the positive, if I plug in 1 for root x, I get 1 again. So 1 times 2 is 2. I'm going to skip ahead now to a perfect square so that the square root's actually going to give us something. If I plugged in 4 for x, I get root 4, which is 2, and then you multiply by the 2 on the outside. So you got 4 if you plug in 4. And then from there we can just extrapolate, like, here's the pattern. Now here's the thing, we've got the exact same expression except it's negative out front. Now this should actually be very simple for us. Everything you just plotted on this graph, make it negative. So we're going to go over 1 down 2 because the front is negated. We're going to go over 4 down 1, 2, 3, 4 because that's negated. So here's the interesting part about this. It almost looks like a sideways parabola. In fact, should I do this? Oh no, it's a parabola. You see? All right, sorry. Motion sickness, I hope that's not happening. So kind of cool. And you can also take the perspective of if we literally looked at it as the original was y equals 1/4 x squared. If we thought about it like this, it's almost like, yeah, that's what it is on its side. It's y equals 1/4 x squared when we look at it from a 90-degree rotational perspective. Cool. Let's go on to 49 now. Ooh, we have a cubed function. So if you remembered, odd functions kind of have this behavior of, I think I used to call them ends. I don't know why that was so difficult to say. But bottom line is that they came from the cubed function that kind of has that same pattern. All right? So this is shifted down 8 units because of the minus 8. 1, 2, 3, 4, 5, 6, 7, 8. From there, you can just plot some points. So if you plug in -1, you get -1 cubed, which is -1 minus 8, all the way down to -9. And if you plug in 1, that'd be 1 cubed minus 8, which is 1 minus 8, which is -7. Now if I plugged in 2. 2 cubed is 8, 8 minus 8 is 0. So that's one of the graph's zeros. From there, you don't need to do much. You just need to know that the pattern is a very pronounced curve that gets exponentially bigger really quick. I mean, if you got space, I'd keep going below that, but I think you guys get the idea. All right, so there's our cubed family of functions. And again, normally, if it's more than just x cubed is minus like a constant, you'll get some weirder behavior like that. All right, on to 51. Oh, we have another square root function. Do we need to do this? Yeah, why not? So this one is y equals root x minus 4. All that is a rooted function shifted down 4. All right? So there's this x minus h plus k structure that really follows most functions around the function spectrum. So it's not shifted left or right at all. It's right based on the origin, but it's shifted down k units, down 4 units. So go down 1, 2, 3, 4, plot a point, and then from there you can say, okay, root 1 is 1, minus 4 is -3. Move on to 4, go over 1, 2, 3, 4. Root 4 is 2, 2 minus 4 is -2. And I guess from there you can plot as many points as you want to, but just know that it's kind of following this pattern of getting closer and closer to the x-axis. It should get to the x-axis at 16, because the square root of 16 is 4. 4 minus 4 is 0. The next one looks interesting. It was one that we really didn't talk a whole lot about last year. Number 53. X plus 3 squared plus y minus 2 squared is equal to 9. All right, this has circular structure. All right, this is a circle. It's not necessarily a function, because a function would not fail the vertical line test that a circle fails. So it's not necessarily a function per se, but I mean, circles are pretty important to the geometry of the world. So how this structure works, you remember the HK business I've been kind of harping on for a lot? This is x minus h, so the horizontal shift of the circle from the origin, plus y minus k squared, which is the vertical shift from the origin, and equals, interestingly enough, the radius length. And it's radius length squared. It seems like the Pythagorean theorem has got sort of like, I don't know, a footprint in this business, right? You know, a squared plus b squared equals c squared. I'm not going to dig too much into that. So what this tells us is that the radius is 3, right? Because 3 squared is equal to 9. The shift is move right 2 units. Remember, it's always opposite of what it is in the parentheses as far as the direction it moves. And then this is 3 units to the left. 3 units to the left. So we're going left 3 units, up 2 units, and then we're going to go in each direction 3 units. Now I'm going to say each direction on a horizontal plane or a vertical plane. So I'm not going to try to test 3 units out in random spaces. I'm going to go over 1, 2, 3, plot a point, up 1, 2, 3, plot a point, over 1, 2, 3, plot a point, and down 1, 2, 3, plot a point. All right, now if you guys had a compass like in the old days, I'd just have you guys make a perfect circle around that. Since we are in 2020 and you guys don't have access to that as readily available, you'll just freehand it. And then technically the dot in the center isn't a part of a circle. It's just kind of like a guiding point. So there you go. Kind of a circle. All right, and then the last one that I'll show in this video for graphing is 55. It actually has, oh man, this marker, where have you been all my life? Y equals negative root, sorry, got a little excited there. Negative root 16 minus x squared. Now, if you think about this, y is by itself, how should I put this? This is a semicircle. If I solve for y, I would get a structure very similar to this. I mean, think about it. Y squared is equal to 16 minus x squared. If I squared both sides, and if I rearrange things, add x squared to both sides, this looks just like a circle. Okay, so this is a version of that circle right there. It's a semicircle. So you'd start, it's not shifted up, how would we say this? It's not shifted right or left or up or down. It's just negative, which means it's going to go below the x-axis. And the 16 indicates that we have a radius of 4. So you'd start at the center, go down 1, 2, 3, 4, over 1, 2, 3, 4, left 1, 2, 3, 4, and you've got your semicircle.